A chain of mountains stretching across the eastern United States holds one of the most concentrated deposits of coal on Earth. Yet the reason for that concentration is not immediately visible in the landscape itself. Why does this particular region, rather than countless others with similar elevations and climates, contain such vast reserves of carbon-rich rock? How did layers of ancient plant material survive burial, pressure, and deep time without being scattered or destroyed? And why does the terrain of the Appalachian Plateau appear so intricately carved, as though the land itself records the process that locked away this resource? In the area southeast of Grundy, Virginia, looking toward Mingo County, West Virginia, the terrain rises and falls in a pattern that seems almost deliberate. Narrow ridges, steep slopes, and branching valleys form a dense network that directs water into progressively larger streams. This portion of the Appalachian Plateau stands apart from neighboring regions, not because of extreme elevation, but because of how its surface reflects what lies beneath. The coal seams that define the region are not randomly distributed. They follow a geological logic that began hundreds of millions of years ago and remains encoded in the rock layers today. The Appalachian Plateau extends across a broad swath of the eastern United States, reaching from parts of Alabama through Kentucky, West Virginia, Ohio, and into Pennsylvania and New York. In contrast to the adjacent Valley and Ridge Province, where rock layers have been folded and faulted into long parallel ridges, the plateau retains a relatively horizontal structure. This distinction is central to understanding why coal is so abundant here. Flat-lying sedimentary layers create conditions that preserve organic material in a way that deformation often disrupts. Coal does not form simply because vegetation exists. Forests have covered large portions of Earth's surface for millions of years, yet only certain environments allow plant matter to accumulate, resist decay, and transform into coal. During the late Paleozoic era, particularly in the Carboniferous period, the region that is now Appalachia lay near the equator. The climate was warm and humid, supporting dense, swampy forests filled with towering lycopsids, ferns, and early seed plants. These wetlands were not isolated patches, but vast, interconnected systems that stretched across low-lying basins. In these ancient swamps, plant material accumulated faster than it could fully decompose. Waterlogged conditions limited oxygen, slowing microbial activity and allowing thick layers of peat to build up. Over time, repeated cycles of flooding and sediment deposition buried these peat layers beneath sand, silt, and clay. Each burial event sealed organic material away from the atmosphere, compressing it and gradually altering its chemical composition. With increasing depth, heat and pressure transformed peat into lignite, then bituminous coal, and in some cases, anthracite. The reason Appalachia became especially rich in coal lies partly in the stability of its depositional environment. The region experienced repeated transgressions and regressions of shallow inland seas, which advanced and retreated over the landscape. Each cycle left behind a distinct sequence of rock layers: sandstone from river channels, shale from floodplains, and coal from peat-forming swamps. These repeating patterns, often referred to as cyclothams, stacked one upon another over millions of years, creating multiple coal seams at different depths. While many parts of the world experienced similar conditions during the Carboniferous period, the Appalachian region benefited from a combination of factors that enhanced preservation. The basin in which these sediments accumulated subsided gradually, allowing thick sequences to build without being eroded away. At the same time, tectonic activity associated with the formation of the Appalachian Mountains influenced sediment supply and basin geometry. The collision of ancient land masses, including the assembly of the supercontinent Pangaea, generated mountains to the east that shed sediments westward into the basin. This influx of sediment played a dual role. On one hand, it periodically buried peat layers, protecting them from oxidation and decay. On the other hand, it created alternating layers of rock with different resistance to erosion. Sandstone units, being more resistant, now form the ridges seen across the plateau, while softer shale layers erode more easily, contributing to valley formation. Coal seams are typically found sandwiched between these layers, their positions reflecting the original swamp surfaces that once existed at those horizons. The present-day landscape offers visual evidence of these processes. Colored elevation maps reveal dendritic drainage patterns, where streams branch like veins or lightning across the terrain. This pattern emerges in regions where rock layers are relatively uniform in resistance, allowing water to carve channels without being strongly guided by structural features such as faults or folds. In the Appalachian Plateau, the combination of horizontal layering and varying rock strength produces a terrain where erosion operates in a distributed yet structured manner. Cities such as Charleston in West Virginia, Pikeville in Kentucky, and Point Pleasant in West Virginia illustrate how human settlement adapts to this complex topography. Flat land is limited, often confined to narrow valley floors along rivers. Urban development follows these natural corridors, with roads and buildings constrained by steep slopes on either side. The same geological conditions that preserved coal also restrict modern land use, shaping infrastructure and economic activity. Comparisons between locations like Prestonsburg, Kentucky, and Grundy, Virginia, highlight subtle variations within the plateau. Grundy exhibits greater local relief, with steeper slopes and more pronounced elevation changes over short distances. These differences arise from variations in rock thickness, composition, and the history of river incision. Where sandstone layers are thicker or more resistant, ridges stand higher and valleys cut deeper. Where shale dominates, slopes tend to be gentler and drainage patterns may appear more diffuse. The drainage system itself is relatively young in geological terms. Much of the plateau ultimately drains into the Ohio River, which developed as a major flow following glacial influences to the north during the Pleistocene. As the Ohio River established its course, tributaries adjusted their gradients, carving into the plateau and deepening valleys. This process exposed coal seams along hillsides and stream banks, making them accessible long before modern mining techniques were developed. The accessibility of coal in the Appalachian Plateau is not merely a function of its abundance, but also its position within the landscape. Flat, lying seams can be traced horizontally across hillsides, allowing extraction methods that differ significantly from those used in more structurally complex regions. In areas where coal seams are near the surface mining techniques have been employed, including mountaintop removal. This method involves removing overlying rock to expose coal seams directly, a process facilitated by the relatively simple layering of the plateau. The effects of such activity are visible even from satellite imagery, where altered ridgelines and leveled summits contrast with the natural topography. These modifications underscore the interplay between geology and human intervention. The same structural simplicity that preserved coal and made it accessible also enables large-scale alteration of the landscape. Globally, the Appalachian Plateau represents a rare convergence of conditions. Other regions, such as parts of the Sichuan Basin in China, share certain characteristics, including sedimentary layering and basin development. However, the specific combination of extensive Carboniferous coal formation, subsequent tectonic stability in the plateau region, and later erosion patterns tied to the Ohio River system produces a landscape that is difficult to replicate elsewhere. The coal richness of Appalachia is therefore not the result of a single factor, but a sequence of interconnected processes. Ancient equatorial swamps generated vast quantities of organic material. Cyclical sea level changes buried and preserved that material in repeating layers. Tectonic forces created a basin that allowed sediments to accumulate without excessive disruption. Later, erosion sculpted the landscape, exposing coal seams and defining the intricate networks of ridges and valleys seen today. Each ridge and valley in the Appalachian Plateau can be interpreted as a cross-section through this history. The height of a ridge may correspond to a resistant sandstone layer deposited in an ancient river channel. The position of a coal seam may mark the surface of a long-vanished swamp. The path of a stream may reflect subtle differences in rock strength that guide erosion over thousands to millions of years. Despite the apparent complexity, the underlying structure remains comparatively simple when viewed in geological terms. This simplicity is precisely what allowed coal to accumulate in such massive, laterally extensive seams. In regions where rocks have been heavily folded or faulted, coal seams are often fragmented, tilted, or buried at great depths, complicating extraction and reducing economic viability. In the Appalachian Plateau, the preservation of horizontal layering maintains continuity, making seams easier to locate and exploit. Yet this same continuity raises further questions about the long-term evolution of the region. If the plateau had experienced more intense deformation, would its coal resources be as significant today? If sea levels had fluctuated differently, would the sequence of cyclothems have formed at all? And how might ongoing processes, including erosion and human activity, continue to reshape the landscape and influence the accessibility of remaining resources? The answers are embedded in the rocks themselves, in the order of layers that record ancient environments with remarkable fidelity. From the dense vegetation of carboniferous swamps to the sediment flows from rising mountains, from the gradual subsidence of a basin to the carving action of rivers, each stage contributes to the current composition of Appalachia. The coal-rich mountains are not simply a feature of the region. They are the result of a long sequence of geological events that align in a way that is both specific and uncommon. As terrain maps and satellite imagery continue to reveal the fine details of the plateau, the relationship between structure, erosion, and resource distribution becomes increasingly clear. The branching patterns of rivers, the spacing of ridges, and the depth of valleys all reflect the same underlying framework. What appears at first glance as a rugged and complex landscape is, in fact, a coherent system shaped by predictable interactions between rock type, water flow, and time. As the plateau continues to be examined in greater detail, the distribution of coal seams reveals a pattern that is both systematic and revealing. These seams are not randomly scattered pockets, but laterally continuous layers that can extend for miles, in some cases stretching more than 100 miles or roughly 160 kilometers across multiple states. This continuity is one of the defining characteristics that distinguishes Appalachian coal deposits from many others around the world. It indicates that the ancient environments responsible for their formation were not isolated swamps, but expansive lowland systems that remained stable for prolonged intervals. The thickness of these coal seams varies significantly, often ranging from a few feet, approximately 1 to 2 meters, to seams exceeding 10 feet, or about 3 meters, in thickness. Such massive accumulations point to long periods during which organic material was able to build without interruption. In many cases, these thick layers are interbedded with shale and sandstone, creating a repeating vertical profile that captures cycles of environmental change. A coal seam may represent thousands of years of plant growth and decay, while the overlying sedimentary layer may reflect a sudden shift in conditions, such as flooding or sediment influx from nearby highlands. The source of that sediment becomes clearer when considering the broader tectonic framework of the region. During the assembly of Pangaea, the collision between ancestral North America and other landmasses generated a series of mountain-building events known as the Alleghanian orogeny. While the most intense deformation occurred in what is now the Valley and Ridge province, the effect of this tectonic activity extended into the plateau. Mountains to the east were uplifted and eroded, supplying vast quantities of sand and mud that were transported westward into the lower basin. This steady delivery of sediment played a crucial role in preserving coal. Each influx buried peat layers under additional weight, increasing pressure and initiating the process of coalification. At the same time, the relatively gentle subsidence of the basin ensured that these layers were not exposed to intense deformation. The plateau essentially functioned as a stable repository, where material could accumulate, be buried, and transform over millions of years without being significantly disrupted. As time progressed, the chemistry of the buried organic material continued to evolve. Increasing temperature and pressure drove off volatile compounds, concentrating carbon and enhancing the energy content of the coal. This transformation did not occur uniformly across the region. In areas closer to tectonic pressure, coal may have advanced to higher ranks, while in more stable zones it remained in lower ranks, such as bituminous coal. These variations are still evident today and influence both the quality and economic value of the deposits. Erosion, acting over tens of millions of years, gradually exposed these layers at the surface. Rivers and streams cut into the plateau, removing overlying rock and revealing coal seams along hillsides and valley walls. The dendritic drainage pattern visible in the elevation maps reflects the relatively uniform resistance of the underlying rocks. Unlike regions where faults or folds dictate the path of rivers, the plateau allows water to carve freely, producing a branching network that expands in all directions. This erosion has a direct impact on how coal is accessed. In many locations, seams are exposed at elevations that make them reachable without deep underground excavation. Early extraction methods took advantage of this accessibility, with miners following seams directly into hillsides. Over time, as demand increased and technology advanced, more extensive methods were employed, including surface mining techniques that remove large volumes of overburden to reach coal deposits. The geometry of the plateau makes such methods feasible. Because the layers are relatively horizontal, removing the upper portions of a ridge can expose a coal seam that extends laterally across the landscape. This approach differs fundamentally from mining in regions where seams are steeply inclined or disrupted by faults, requiring more complex and costly operations. The efficiency of extraction in Appalachia is therefore closely tied to the same geological simplicity that preserved the coal in the first place. However, this simplicity does not imply uniformity. Local variations in rock composition, thickness, and structure create noticeable differences in topography and resource distribution. Near Grundy, Virginia, the terrain exhibits greater relief, with elevation changes of several hundred feet or more than 100 meters occurring over short horizontal distances. This ruggedness reflects thicker or more resistant sandstone layers that resist erosion, resulting in sharper ridges and deeper valleys. In contrast, areas such as Paintsville, Kentucky, display a somewhat more subdued landscape, where valleys are broader and slopes less steep. These differences can be traced back to the original depositional environment and subsequent geological history. Even small changes in sediment supply or basin subsidence during the Carboniferous period can lead to significant variations in the modern landscape. The position and thickness of coal seams are therefore closely linked to these localized conditions. The drainage system of the plateau provides further insight into its development. Streams and rivers ultimately feed into the Ohio River, which acts as a major collection point for water flowing from the region. The Ohio River itself is relatively young, having established much of its present course during the late Cenozoic. Its formation influenced the direction and gradient of tributaries, accelerating the incision of valleys and enhancing the exposure of underlying rock layers. This process of river incision continues today, albeit at a much slower rate than in the past. Over thousands of years, streams gradually deepen their channels, removing material and reshaping the landscape. While the overall form of the plateau remains stable, these incremental changes contribute to the ongoing exposure of coal seams and other geological features. The landscape is therefore not static, but part of a continuous cycle of erosion and adjustment. From a global perspective, the Appalachian Plateau occupies a distinctive position. While other regions contain coal deposits formed under similar conditions, few exhibit the same combination of massive, laterally extensive seams and relatively undeformed structure. In many parts of the world, tectonic activity has folded, faulted, or metamorphosed coal-bearing rocks, complicating their extraction and reducing their continuity. The plateau, by contrast, preserves a clearer record of its depositional history, making it an important reference point for understanding coal formation. The comparison with the Sichuan Basin in China highlights both similarities and differences. Like the Appalachian Plateau, the Sichuan Basin contains thick sedimentary sequences and has experienced long-term subsidence. However, its tectonic setting and subsequent geological evolution differ in ways that affect the distribution and accessibility of resources. The Appalachian region's specific combination of Carboniferous age deposits, tectonic influences, and erosion patterns creates a landscape that is difficult to replicate elsewhere. Human activity has introduced an additional layer of complexity to this system. The extraction of coal has altered the surface in ways that are visible across large areas. Mountaintop removal, in particular, has reshaped portions of the plateau by flattening ridges and filling adjacent valleys with excess material. These changes affect not only the visual appearance of the landscape, but also its hydrology, soil composition, and ecological dynamics. Despite these alterations, the underlying geological framework remains intact. The same layers that formed hundreds of millions of years ago continue to dictate the behavior of water, the stability of slopes, and the distribution of resources. Even as surface features are modified, the deeper structure persists, guiding both natural processes and human activity. The intricate relationship between geology and topography becomes especially apparent when closely examining high-resolution terrain data. Elevation models reveal patterns that are not immediately obvious at ground level, including subtle variations in ridge spacing, valley orientation, and drainage density. These patterns correspond closely to the arrangement of sedimentary layers, reinforcing the connection between ancient depositional environments and modern landscape form. For viewers who want to keep exploring topics like this, stay connected. Like, share, and subscribe, and tap that hype icon to help this reach a wider audience.